All right, it's 4 o'clock, so let's get started. I'm sure more people will trickle in. Last year, this session, it wasn't myself that was delivering it, but there was another multiprocessing session that was in this same room and had the same lack of seats. So if you don't mind, if you're leaving a review for this session, just mention that it was full. So hopefully next year we can maybe get a bigger room and get seats for everyone. But anyway, so with that said, my name is Clinton, and I'm here with Neeraj. I'm on the geoprocessing team, and he's on spatial analyst. And we're here to talk about multiprocessing with ArcPy. Just a quick note about the title. There is actually a Python library called parallelization. It's been a little bit out of service for a while, so this talk is not about that, just in case anyone is under that impression. Let's just move forward here. So we'll talk about several things today. First of all, just a quick discussion about what multiprocessing actually is and what it isn't. I find that there's a lot of, I don't want to say confusion, but maybe misinformation out there about how things work. So I just want to clear that up a little bit, then actually show a demo of some of the multiprocessing modules in pure Python. Then from there, we'll start discussing the concepts in the context of GIS. And at that point, move into some demos and examples of code that we have. And moving forward, just discuss the path ahead for multiprocessing with ArcPy and a little bit of some considerations and best practices and so forth. And then we'll finish up with the resources. If you do have any questions, please just hold them to the end, and we'll leave some time to answer some questions. So just the first thing I just want to quickly address here is that multiprocessing and concurrency often get confused, and they're not the same thing. So multiprocessing is essentially running multiple processes at once, while concurrency is running multiple instructions within a single process. So we'll explore that a little bit more. But just to also speak about the infrastructure that you're working on, multiple computers, of course, have multiple CPUs. So you're essentially, switching from a paradigm that's almost like a single-track road to a multi-lane road. And the ArcPy was designed in a time when Python really didn't have a lot of good multiprocessing support. So there's a lot of things that are kind of inherited from the legacy code that we're working through right now to enable that. So the beginning of this presentation will cover more about the current state of things, and then discuss the actual the changes that we're looking at as well. So as I was saying before, you can kind of think of as your program is either a road or a highway, but there's also a good analogy in sewing threads as well, and you'll see why in a moment here. Essentially, you can think of all of the instructions in your program as a single fiber within a thread, and they get twisted together as you move them between processes. So essentially, if you think about a thread, that there's something that has to hold it together at either end, and then it, as I say, gets twisted. So you can almost think of that as the functions that actually bind the multiprocessing and hold it together. And essentially, the second knot can either be a process of aggregation, or it can also chain into another process, which is almost kind of like braiding those fibers together. And with that, you can actually begin to chain multiple processes as well. So just another example, I know a lot of geographers are here. So I'm not from Southern California. Is anyone here from Southern California? Or just quickly put up your hand. Yeah, so a few people, most of you aren't. I'm originally from Canada, and we have a single highway that goes across the whole country, just one. And if there's an avalanche in the Rockies or a blizzard or something like that, the whole thing gets cut down. So if trucks are trying to go across, there's nothing that they can do. So essentially, that to me is like the single lane road, like I'm saying. Meanwhile, when you're here in Southern California, there's essentially what I consider to be one of the wonders of the world in the highway system. And the reason for that is because it's it really inspired me to think about multiprocessing in a different way. If you look at these highways, they're multiple lanes. So if there's an accident in one lane, it can get shut down and traffic can continue to flow through the other ones. So it's got fault tolerance built into it. There's also these complex interoperations, or clover leafs, that essentially have a whole bunch of off-ramps and on-ramps that allow traffic to move between these corridors. And then additionally, the cost of infrastructure is something to be considered as well. So in a country like Canada, where you have a lower GDP, we can only afford to maintain that one highway. But in a place like California, where there's as many people here as there are in all of Canada, it's much easier to afford those large highways. So that's kind of analogous to who will be using, or how many people may be using your application. If it's a simple one that doesn't have too many people using it, then you probably don't need multiprocessing. However, if it's a large application that has a lot of data flowing through it, or a lot of users, then you definitely want to consider multiprocessing as an option in your design. So just on the other side, what it isn't, and I won't spend too much time on this, but like I said, so it's definitely not a serial program, and that's where we're coming from in ArcGIS. So it's important to remember that there's that disconnect there. It's also not concurrency. It is important to recognize, though, that those are actually complementary things. So if you have a concurrent multiprocessing program, then that you're actually getting the most out of each process. It's also not a decentralized program, so that's more of like a server-based architecture, like Skype or something along those lines, and not distributed. The reason I bring up distributed, however, is there's a great new Python package out there called Dask, D-A-S-K, that's put out by one of our partners, Continuum Analytics, and it's great for just distributing, your programs, and also working in parallel on a single machine. So there is a talk about that tomorrow on Thursday by Brendan Collins from Continuum Analytics, and I'd definitely recommend that you check that out if you're interested in taking this to the next level. So if you were to have a perfect multiprocessing system, you essentially want to look at replacing all of your loops with parallelized iteration, replace all of the collections that feed those with iterators or generators, and combine, like I was saying before, multiprocessing with concurrency. So if you're considering the highway analogy, what that essentially lets you do is have drivers in every lane, and then when one of the drivers gets tired, it'll switch to the other driver, so the car just can keep on going without causing any delays. There's the fault tolerance that's analogous to shutting down one lane. So essentially having all of these different processes, if there's an error in one while you're doing the exception logic of that error, the rest of the program can keep flowing. There is, however, the consideration that you will have to route that traffic, so there's not a backlog as well. So that's something to consider when you're looking at the larger design of your program. And obviously, these won't apply to every single program. I mean, this is in a perfect world, but there's always considerations that can throw a monkey wrench into the works. Let's see here. So there's, as I mentioned, there's also the two types of output. So essentially, the way I look at that with the highway analogy is it's either putting it into another city's system or delivering each one of those cars safely home. Okay, so now I'll just quickly discuss the actual modules that are present in pure Python. The first of which I want to talk about is threading. So this one I see used fairly often, but it's actually a very, very specific package that's really only for core developers that are actually making an underlying framework or package or something like that that is to support threading. But there's some inherent problems with it. I'm sure many people here, if you're experienced with Python, have heard of the global interpreter lock. And that's essentially, one of the reasons that Python gets a fairly bad rap in some circles is that you can't actually natively concurrently run 2 Python instructions on the same thread. And if you think about that, Python is an interpreted language. So if you have your car driving along, you have 2 people in there, but both of them have a job. There's the interpreter and then the driver, so to speak. So they can't switch back and forth. One of them can't go to sleep because then the whole thing will crash. So kind of like if you're trying to drive in a city with signs that have different language that you're used to. So to get around that, Python has put the multiprocessing package in place. And what that does is creates multiple Python processes, as the name implies. But because there's multiple instances of Python, they're not subject to the global interpreter lock unless you're trying to do concurrency on those threads. So at that point, you can kind of start thinking of the operating system as the system that's implementing the threading module, if you will. On the other hand, there's a subprocess, which, well, technically you can use to launch Python instances, but typically it's used to launch non-Python processes. That can either be done in a serial fashion, where you're halting a single thread, running a second one, and then letting that go again. Or it can be run where the first process calls the second process, they both run in parallel, and then the second one either signals to the first one to let it know that it's done, or they both just finish and essentially pipe that into another process. Now, these 2 modules I just wanted to talk about briefly as well. Twisted is the previous Python package that deals with the threading and concurrency, and it's been replaced in Python 3.5 and 3.6 by a module called async IO. Now, they essentially do more or less the same thing in helping get around the global interpreter lock. And essentially at that point, it's replacing some of the calls in there for the interpreter with a C call to kind of get around that limitation. So let's see here. I'm not trying to say that async IO is completely taking over what Twisted does, because there's actually a lot of inbuilt functionality in that. So if you're looking to, for example, to do concurrency with video, for example, or audio or something along those lines, then Twisted has built-in functionality that can allow you to do that. Move forward. So I've just got a quick little example of how multiprocessing actually works in the command line. And essentially, it's just running all 4 of those lines in a separate process. So you can see on the right-hand side there that each one of them has a slightly different delay. So the first one is got 2 seconds, 4 seconds, 1 second, and then 8 seconds. And they're all moving forward kind of at that rate. So essentially, just in the code there, if you can see the first line with the data, so that's just setting up a very, very simple data set and giving each one of those a title and then the actual delay. And then the position is being set by the enumerate function on that data. So the important thing here, however, is on the third function, the MP handler, you can see that there's multiprocessing.pool, and that's actually creating, as it suggests, a pool of processes that you can pick out one at a time and start to work with. So in the second step, I'm using the map function, which takes all of those processes and then maps a specific piece of data to it, and then uses the MP worker function to do what you're seeing on the screen. Now, on the other hand, this is a sub-process. So kind of following with that traffic analogy, it'll get to a certain point, kind of hits a red light, so to speak, And then right here, I'm listing all of the conda packages that were installed in that environment. And you can almost think of that as the red light goes, then it's the other dimension of traffic that's going the other way. Then that red light turns on, and this one keeps going. I won't talk too much about the code, as it's more about multiprocessing, but I just wanted to illustrate that. And then also just quickly with concurrency. So here we've just got a single thread, so you see that there's not multiple progress bars or anything along those lines. And at first, it's creating them all in sequence, so from 0, 1, 2, 3, and 4, and then has a delay just on the side. So as you can see there's several delays, so we should see 0 and 4 first because they're the lowest. And sorry, just let it loop again here. And then 1 and 2 and 3 followed by one another. So that's just to illustrate that they're coming in a certain order, and then again, kind of like when people are driving along a road and passing one another and doing that, then they'll end up at their end result in a different order. And you can also anticipate what that order is if you understand the amount of the delay. So now I'll just pass things over to Neeraj to talk about.
All right. Okay. Hi, everyone. My name is Neeraj. I'm a product engineer in the spatial analyst team. Clinton gave us some fundamental introduction to the different Python modules for multiprocessing and some of the concepts of multiprocessing and concurrency. Now we look at how these concepts are relevant to GIS and how we can use some of them with the ArcPy module. We'll start out with a few concepts on raster datasets and how we can work with rasters. We'll also look at a demo. And after that, Clinton will look at some concepts for working with vector datasets and a demo on how to work with vectors. All right. So GIS is the language of geography. Profound words by Jack from Esri 2004. And we all know that Python is the language of GIS. However, combining program with geography raises a lot of complications, and you have to work with projected data, and you have to take your UI into consideration. So those are a few challenges you face combining programming and geography. So what are the challenges working with the multiprocessing module and working with GIS? So we'll start out by looking at what the concepts in raster datasets are that are easily parallelizable. So I've identified two candidate operations that can be easily parallelized. The first one we look at is how to parallelize independent tasks within a workflow. So what does this mean? In this diagram here, what you see is a workflow. This would be something that you might do in, say, a suitability model. To do that, you're going to run a series of tools. In this example, I'm running the slope tool, the aspect tool, and the reclassify tool. And finally, I'm combining those outputs with the weighted sum tool to get my suitability raster. So in this example, if you were to run this process through ArcGIS Pro or ArcMap or in Model Builder, or if you even wrote a standalone script, you're usually going to work on this in a serial fashion. What this means is that you have one worker process, and this worker process can only execute one tool at a time. So it's going to complete the slope tool and then move on to the aspect tool and so forth, as you can see in this timeline. However, looking at this diagram, you can identify that there are independent tasks within this workflow that have no dependencies on each other. For instance, the slope tool's execution, the aspect tool's execution, and the reclassified tool doesn't have any interdependencies, whereas the weighted sum tool has to wait for these three tools to complete executing before it can begin its process, because it has to wait for those three output rasters to be created. Okay? So now that we have identified those independent tasks, how do we go about redesigning this problem to approach it in a parallel fashion. You might do something like this, where you're going to now leverage all the processes, or as many as you could, for such a task, and you're going to execute your independent tasks simultaneously, and then the weighted sum tool, which is a dependent task, has to wait for all those dependencies to come through before it can execute. And doing this will give you considerable performance improvement. So what is the second class of operations that you might want to parallelize? This is when you're working with a really large raster data set with potentially billions of cells. And the method that I'm going to show here today is limited to local, focal, and zonal raster operations. So let's digress for a moment there and understand what these different types of raster operations, the local, focal, and zonal operations are. All right. So there are essentially 4 types of raster operations that you can bin your different operations into. So the local operation is a per cell function where the result at your output is going to depend on the value of the input cell at that location. Then moving on to a focal operation or a neighborhood operation is one where the result at that output cell is going to depend on the input value at that cell and a neighborhood around that cell. So that neighborhood could be a 3x3 window around that cell, or it could be any neighborhood that you might choose to define based on the type of process you're running. So if you have used the neighborhood toolset in the spatial analyst toolbox, like focal statistics, those are all neighborhood functions, or even if the slope tool or the aspect tool, those are all focal operations. Zonal operations are a type of focal operations, only that now your neighborhood is a larger zone, which could represent a cartographic zone. This could be something like a land use type, or it could be a watershed. So in those cases, your result at the output cell potentially depends on all the values within that zone of the input, right? And finally, we have global operations, which we won't be looking into how to parallelize those type of operations. Global operations are per raster operations, where the result at that output cell could potentially depend on the input values across the entire input raster, right? So how, now going back to addressing the parallelizing of a large raster data set, how would we go about this process? So if you were to simply run a tool, say a local operation, I'm going to look at a simple example of a square root tool. And if you're going to run a large data set, you would simply provide it as an input parameter and run the tool. But this could potentially take a lot of time. And if this is a repetitive process that you're doing on a daily basis, or you're scheduling this task to happen, say you get some data from a server and you pull it and you're going to schedule it every night to run, speeding this up would give you some gains over the time, right? So how we can do that is by splitting our domain up and leveraging multiple workers in our machine, which work on different extents of your input and would write the output to those extents. And this way, the whole process faster, because now instead of just one worker, we have 4 workers in this example working across the data set, all right? So now let's move on to our demo and see how actually you might do this through Python and what the code looks like. So I'll start out with this workspace I have here, and within this workspace, I'm going to quickly explain what all I have in here. I have a folder called fishnets, and in here I'm going to create fishnets or grids that decide how I'm going to chunk or chop up my data and send it to different processors. So this would simply hold a feature when I'm completed running my script, all right? the local raster workspace that would hold the outputs from those individual processes processing the different extents of your input. The mosaic dataset, the local function mosaic, is going to reference all those individual outputs that were created, and it's going to store it so that your output dataset resembles the input. And finally, you have your input raster, which is the one that you're going to be running your raster function on. All right. And we have a script to go along in this directory, which is, I'm calling it a parallel local. And this is a Python script. So let's see what this script looks like. All right. I'll give you a moment to go through that. And what essentially we have here is the whole script. I have collapsed some of the functions at the bottom and the main module of this script. So in the top of the script, I'm grabbing all the necessary modules I need to carry out my task. I need the ArcPy module. I'm going to need the multiprocessing module to spawn up different multiple processes. I'll need the logging module to print these results to the screen and give you some idea of how long things are taking. And in the next step, I'm setting some environments. I'm going to need the spatial analyst extension because I'll be running the spatial analyst square root tool that we spoke about in the previous slide. And I'm going to make use of the in-memory workspace to write intermediate data sets. In the next block, I'm just creating a logger that's going to report how these processes are running and how long they're taking to complete. And then I have some paths to my input raster dataset and the output fishnet dataset where I'll write my fishnet features once I create them. Okay. So let's go through each of those individual functions. We'll start out with the main and go through that first. Okay. So within the main module, I'm going to call my fishnet tool by calling the create fishnet function. We will look at that in the next slide and see what exactly is going on there. After that, my fishnets have been created. So this is a feature class, which is simply a grid of the input extent. And once that's created, I'm going to go and grab the extents from each of those individual geometries which are within that feature class. And once I grab those extents, I'm going to create a list out of it and pass that as an iterable to my execute task function. So that is where I'm creating a pool of workers. And there I'm specifying that my pool should have as many workers as my number of CPUs by using the CPU count function. Once I do that, to the pool, I'm mapping the execute task function. Execute task is where the actual GP heavy lifting is done. That's where your GP tool is going to be executed. And to it, I'm passing a list of those individual extents that each process would have to work on. All right. So we'll get to the execute task function as well in the consequent slides and see what exactly is going on inside there. Once all that is complete, I'm just going to create a mosaic from all those individual chunks that were processed. And after that, you're done. You have your output result. So let's take a look at the create fishnet function. And this is a very simple function. I'm just executing one tool in here. This is the create fishnet tool. And this is a very handy tool if you're working with multiprocessing and you need to divide your workspace. And it helps a lot even with features if you're going to work with features. The nice thing is you can decide how many rows and columns you want to chop it up. So here I'm choosing 4 rows and 4 columns. So totally I'll have 16 chunks of data that I'll be processing. I'll be giving the fishnet tool also the extents of my input raster so that it knows where to create these fishnets. All right, so now let's look at the execute task function. This is where the GP tool is going to be executed by the different worker functions. And so you can notice here that I'm only passing a list of those extents and not the extent geoprocessing object itself, because geoprocessing objects are not pickable. And what this means is that you won't be able to send them across the wire from your main process to those child processes that are running on the individual extents. And to overcome this, I am working with a simple Python type, which is just a list. And I'm boiling down those extents into the list. And once I'm within my worker function, I'm putting them back together as an extent. So what's going on within the, once we grab those extents, you are going to set a few environments. You need to set your snap raster environment and your cell size so that your output isn't resampled or shifted about. I am also going to set the processing extent that I pass to this function so that this worker process is only going to work on that particular extent of my large input data set. After that, I'm going to run the square root tool, the spatial analyst square root tool. This is the actual tool execution. And once that is done, I'm going to write that output to disk. So until this stage, all the intermediate outputs are handled in memory because I set initially in as my Scratch workspace, which was the in-memory workspace. So that means you're not writing back to disk and reading again, and that's going to slow the whole thing down. So we are leveraging the in-memory workspace to write temporary data sets, and that will give you good performance gains. All right. And that is the execute task function. So what happens when we run all this? I'm going to run it, and first I'm going to create the fishnets, and that's going to complete. And then when I create my process pool and send it the different extents that each process has to work on, it's going to spawn these different processes you can see here, 1 to 8, I think. And that is the number of cores in my machine. And once that, so you can see that as soon as any of those workers complete, it goes and picks up the next data set that it has to process. In this case, I have 16 chunks and I have only 8 processes. So as soon as any one of those processes completes its task, it's going to go grab the next extent that it has to work on, and it's going to process that. So there is no waiting around for all the other processes to complete. It's parallelized in that sense. And this whole task would take about 114 seconds for a local function that I ran. And when it is complete, it's going to write all those output data sets, as you can see, and the mosaic is going to reference each of those individual bits. So your final answer is the same extent as your input data set. All right. So what is the point of doing all this? I could have simply run the GP tool and be done with it. What if it takes, what's the big deal if it takes a couple more hours, right? So this is the whole reason to go about this process. You, as I had mentioned earlier, you might only want to do this if it is a repetitive task that you're carrying out on a regular basis, or it is part of a bigger workflow that you execute quite often. And by doing this, you're going to get performance gains. So as you can see in this graph, I'm looking at how the performance is changing for a focal function as I increase the number of processes. You can see that initially going from 1 to 2 and 2 to 3, the jumps, that is the performance gains, are much more than subsequently. And the reason for this is that as you are spawning up more processes, the overheads of doing that is going to negate the benefits you're going to get by these multiple processes working simultaneously. So it's really a trial and error process where you will have to understand what is the most optimum number of processes that I need to use for my task that will give me the most performance gains and not choke up my system resources. So in this case, it's about 4. All right. So what you're looking at now is I've also plotted what the performance looks like for a local function. And as you can see, there is a slight difference between the gains for the local and the focal function. This is because your focal function is a neighborhood operation and is inherently more intensive computationally. So if you leverage parallel processing, you see that the gains there are more than if you were to do it with a local operation. Right. Okay, so Clinton will continue with some concepts on vectors.
Thank you very much. And just something just came to mind as you were talking there, so I'll just quickly say it. As far as the number of processes and the overhead is concerned, again, going back to the highway analogy, that's almost like when people are trying to move from the left lane into the right-hand lane to merge. You don't often see highways that have more than 4 or 5 lanes because it's very difficult to get across if you need to. However, you do see those lanes as being things like carpool lanes or express lanes, and that is where you may be able to leverage more than 4 cores, as if it's kind of just blasting through there, but not doing the interoperation between the disk and the program. So with that said, I'll move over to vectors. And vectors are inherently a little bit easier than rasters in some respects, simply because they're discrete units of data. They're not a continuous unit of data, so they're easier in some ways to split up into actual groups or batches. And as an aside, when you're running a batch process, it's kind of doing the beginnings of multiprocessing, in that it's breaking up a process into multiple functions that you're going to run. However, it's running those serially, so you need to, at that point, take those batches and kind of pivot them so they can be run in parallel. So as I've mentioned before, you've got the aggregation step at the final end. And that's a very important thing to consider, because you don't want to essentially have that be a bottleneck. You don't want all of that traffic to be flowing into a single point that prevents the traffic from actually moving through it. So you really want the aggregation steps to be the minimal amount of actual processing functionality, and you want to put as much as you can into the multiprocessing part of things. So essentially, once that aggregation step has been done, and it doesn't necessarily have to be a single step as well. You can aggregate and then aggregate again. So at that point, you can even start piping multi-processes together. So a simple example of doing that, putting most of that logic in the multiprocessing point, is to have a collection of a bunch of points, split them into batches, then project those points, aggregate them as an array, and then the aggregated array becomes a line. Meanwhile, if you're looking at returning discrete results, a better example for that would be splitting up points into those batches again, and then running a geocoding function on that. And at that point, you're just returning independent addresses, which are the discrete units, rather than recollecting them or aggregating them. Let's see here. So for this example, I've kept it a little bit simpler than Neeraj's. I let him do a lot of the comparison, and this is just more so to illustrate the concepts. So up top, you can see we've got a collection of ranges, and what that represents is a batch of object IDs. That's akin to fishnetting your raster. That's setting where those boundaries for the different collections are going to be. And again, creating a pool of multiprocessing. You'll see that used quite frequently in examples, not just here, but also online. It just tends to be the easiest with map, unless you're trying to run different functionality on each of those. But if you're trying to do the same thing to each one of those batches, then map is definitely the way to go. That name is taken from MapReduce, if you're familiar with that concept. It's a Google algorithm that they use for parallelization, and it essentially, the map part of it means for each one of those batches, map it to a function. So it's sending it to that function, and then it'll execute across the whole thing. And then the reduce step is that aggregation that I'm describing. So it's essentially reducing the amount of data into information that is based off the functions that you put it through. So in here, then you can see, I'm actually going to jump forward and then jump back. The worker process in this case is generating a near table. So it's essentially taking a million points, chopping those up into those batches as you saw, and then for each one of them, generating a near table for 300 points. There's just a few important things to mention in here. So you'll see that I'm actually using the ArcPy.management.make feature layer naming convention as opposed to the underscore, or it'd be make feature layer underscore management. And that's to actually extract the function itself from the underlying structure of ArcPy. The other way around, it's importing that through a series of import and init files, and it doesn't work quite as well. It's not as clean as a breakoff, and if you're using that naming convention, it can actually introduce some overhead that doesn't need to be there. And then also an important thing to note is just on the second function where it's the generate near table, it again is using the in-memory workspace as the intermediate step before aggregation. And again, that's to get away from the bottleneck of disk input-output, and also just to speed things up. But you do need to be mindful of the amount of memory that you have. You can't obviously put 30 gigabytes of memory if you've only got 16 on your machine. So that's where I say you need to consider generators, where you can actually put individual units of data through your machine and then write them before the next one gets put in. And then at that point, you won't actually ever see the memory footprint of the process increase due to that reading of data. And then, so as you can see on the final few steps here, then it's just putting that back into a NumPy array and then returning the actual result array at the end. And then after that, deleting the in-memory table. Now, so the reason it's returning NumPy arrays is for the aggregation step. You can see that there's the numpy.concatenate function, and that's just where it's taking all of those arrays and then in a very fast fashion putting them into a single array. And it's also worth mentioning that NumPy is very handy for multiprocessing because it's a very optimized mathematical library. So if you're trying to do things like concatenating an array, it's much faster to do it in NumPy than it is to do it in pure Python. And that's because it's been optimized at the C code level to do these things. So once that's done, then I'm also just closing and joining the pool. And join essentially just means bringing all those processes back together to ensure that there's no errors that have been left over inside it. When you're trying to do that, if one of them does have an exception, then it'll pass it back up to the main function at that point in time. Or I should say the main process, sorry. And then this example here is just very quickly to show that batching can be done on other dimensions of your data, not just the object ID. So you can see there's the SQL variable there is actually defining a statement which will look for a number of different of the actual fields on the feature and then batch them accordingly. So just a few best practices to working with multiprocessing in ArcPy. As we've mentioned a few times, use in-memory workspace to store your temporary results. It will vastly increase the speed as opposed to writing intermediate to disk. Also, currently file geodatabases and grid raster types are somewhat difficult to work with. You can read from them without issues in multiprocessing, but to write to them often can cause schema locks or synchronization issues. So again, that's why all of those are putting them into that intermediate step of different shapefiles, different geodatabases, so on and so forth. And then once you're sure that the lock is no longer present, you can move on to the next step. If you are coming from the 10x world of ArcMap and ArcCatalog and so on and so forth, as I mentioned before, they're coming from an older paradigm of Python. So there's been a lot of development in the past 10 years or so that ArcPy has been maturing in. So about halfway through that, I didn't work here at that point in time, so the geoprocessing team added 64-bit geoprocessing and background geoprocessing, and that's essentially using subprocesses, as I had mentioned earlier, to create that extra Python process and then run stuff in parallel, and then it'll send a signal back to let the main application know that the process is done, and then the result object will get populated. It's also just worth noting that if you are working on 32-bit machinery, I know that's not so much of a concern anymore, but sometimes it is, that there's a strict limitation with your RAM of just above 3 gigabytes. So if you are trying to leverage a larger amount of memory, 64 bits definitely the way to go as well. And this is the part I've been looking forward to, what we're wanting to do with multiprocessing in ArcPy. So it's essentially a lot going on under the hood right now with what we're doing with Python. And one of those things is decoupling Python from the application. So as you've probably seen today, ArcGIS Pro can now be run side by side, so you can actually have 2 instances of it running. And this will enable us going forward to utilize multiple processes that then call multiple multiprocessing instances. Right now, that's not really something you can do, but moving forward, that should be more and more of an option. And that's kind of like when you're reaching that limit, you can't add more lanes to your highway, so you just build another highway. It's that same kind of idea. If you've got that much data flowing through where you're in a big data type situation, you may actually need all of those to handle everything coming through. Additionally, more asynchronous support in Python itself should be coming through as well soon. I don't have the exact release date that will be coming through because, as I say, there's a lot of work being done. It won't be in 2.0, but we're hoping 2.1. May have to be 2.2, however. So with that said, what that will do will really speed up your tools. I mean, it's actually quite important because if you have a large data set, it will allow you to read that while processing the tool. So it's no longer you have to wait for that whole thing to read, then process, and then wait for the whole thing to write, but they can start to mix together. And that essentially allows the whole runtime of the tool to start to compress. And also, services are certainly something that you can use right now with ArcPy. That's not a question, but it's just going to get better from here. So services are very intuitive to use with multiprocessing because they're multiple processes. They're not even on the same machine at that point, but they're processes that are spread across a data center or spread across even multiple machines that aren't otherwise related. And those machines can then start to be chained together too, which is a process called data pipelining. So we're hoping to move into that area as well. And essentially open things up online and move into more of a service-oriented architecture. So we do have just a few resources here as well. So the first one, of course, is the actual demo that was done by Neeraj. And the second one is a blog post that I got my example from that was done a few years ago. We are going to come out with a few more blog posts over the next, 6 months or so, that will deal with this in a lot more detail too. And let's see, there's the Python multiprocessing API. That's, of course, the documentation that Python provides, but there's actually a lot of gems in there if you read through it that really explain programming. So we've got about 10 minutes left here, and that's intentional for any questions that anyone wanted to ask. You're welcome to ask away.
All right, we have a question over there. Let's pass around to Mike.
Yeah, we can pass around to Mike. So it is being recorded, just so you know. And if you're not staying, thanks very much for coming by. We do have the Dev Summit application, and feel free to leave any comments or anything like that on your review of the session.
So I have one small question. One thing is, will the table to number array also handle geometries? Will it be able to convert the geometries into NumPy array and back and forth?
Yes, so it's converting that entire table. So every field within it should be converted over. And, or wait, no, actually that's, I actually believe it won't, now that I think about it. I don't think it'll hold the strings in there. It may just have the object IDs, and then you'd have to link them back after.
And one more small question is that whether the Esri tools for Hadoop, does it also use the same process, or is it an entirely different way of doing things?
So are you asking if Hadoop itself runs multiple Python processes?
Esri has a sort of geoprocessing tools for Hadoop interoperability. So does it do the same, employ the same mechanism, or is...
That, I don't work on that specific product, so I can't say 100% sure, and I don't want to misinform you. Mm-hmm. If you do want, however, I can introduce you to the big data team after this, and they can answer that for sure.
Thank you.
Can I see the last page again?
Yeah.
Thanks.
There you go.
Anybody have a question? Oh.
So how do you know that you've got efficiency gains? I guess I'm asking more as a Python question.
Mm-hmm.
Because if you're only sub-processing, you're not guaranteed to be on another core, is that correct? Because it's not the same as threading, or is that?
Right. Yes, so as far as that's concerned, you're wanting to know how to measure those gains, or is it like a comparison of multiprocessing versus sub-processing?
Well, just curious to see how you can make sure to guarantee that you're going to always have the gains, because if you have like an overnight processing that's occurring, if you can't fork a thread to make sure that you're on a new CPU core and you're sub-processing, the kernel might do concurrency and not actually operate on a new thread.
That's correct, yeah.
So is there any way to kind of guarantee efficiency gains?
Let me think. Well, so I would say that the first thing that comes to mind right now may actually be the Dask library, just as it actually does all of that work under the hood to ensure that it's being parallelized. So while you could implement it yourself, and it's certainly possible, that's a very large-scale project, and the fact that it's already available out there free of charge is, something that's good to leverage, in my opinion. Outside of that, however, I don't know if there's a pure Python implementation without downloading a package that ensures 100% that it's always going to be the case, because that's done at the OS level. So from the Python side of things, I think it would be very difficult to provide that functionality just based off the fact that it works on all these different operating systems. That said, I will look into that a bit further, and we can include it in the blog post, or if you'd like, I can follow up as well.
Right, I'm going to go to that gentleman first.
Is there any way to get around the locking issue on the file geodatabases for multiprocessing? And what is the earliest version of Python that the multiprocessing library was available?
So with the locking issues, I would say, as we mentioned, it's the writing to those data types that's going to cause your schema lock issues, whereas you can read from them. Is there a way to overcome those locking issues? Not that I'm aware of, at least when you write to, if it's a feature type, then I suggest using shapefiles, and if it's a raster data set, you can write it as a TIFF data set or one of the other types which don't have schema lock issues.
Right. So there is also the option of using an intermediate type of data set that's not native to ArcGIS, such as a GeoJSON file, and then at that point using those to aggregate as well, and that can also increase the interoperability if you do want to utilize that with non-ArcGIS products.
So one workaround would be if all your different processes aren't trying to hit the same file geodatabase, if they're different FGDBs, then you wouldn't have any lock issues. But if it's that one single FGDB into which you want the aggregation to happen, then you're going to experience locking issues. Yeah.
Right.
So that could be a workaround.
And as far as multiprocessing, it started in 2.6. I just searched that.
2.6? Yep. Okay. All right.
And we had, one other question up here.
Here, there you go.
Do you have any suggestions for using the multiprocessing module when you're doing web requests?
Yes, generally it's a good idea to do because they're all, on different machines, so they can all process those requests independently. At that point, again, it's kind of a question of how much is coming through those requests and if that end step can handle it. And if not, then can you do something like create a queue in that end step that can get packed full of information and then get processed, or if there's some way basically to handle that in a single computer when you're pulling from multiple services.
What about if you want to avoid the appearance of totally destroying a website, for instance? Like, I want to send 65,000 requests to a website and get back data.
Right. That would be a great place for generators. So that kind of just puts one piece of data through at a time. So if you want, you can put a delay in that process and then just put an extra second in between each one, and so it starts going a lot slower. That of course would significantly slow down the process, but if that's the point, then that's a good thing, I guess. So
maybe send 100 requests at once, but delay between the next 100.
Yeah, exactly. Yeah, you can create a batch, then put it, the time.sleep, the Python time module, and then just put however long it needs to be in there. And could even, it's getting complicated, but you could even wait for a response from the web server too, and then let that trigger the next batch to go into. So. Thanks. You're welcome.
Thank you. Any other questions? We have a question over there.
Yep. Oh,
one gentleman over here.
One on each side here.
Okay. All right. There you go.
So you mentioned it was more efficient to put everything in memory. What about trying to offload memory to SSD drive? Have you tried that, and does it yield to really interesting performance gains?
So yeah, I could answer that. And yes, I have tried initially when I wrote my script. I have my mic here. Initially, when I wrote my script, I was writing all those intermediate data sets to disk. simply because I wasn't setting my Scratch workspace environment to the in-memory workspace. I just left it to be by default. And I did see that that was a big bottleneck. So using the in-memory workspace to write those intermediate data sets, and I also timed it so I could see that there are gains by using the
But what
in-memory
about
workspace.
not in memory, but on a disk, on a hard drive, but that would be SSD. So let's say your computer
yes,
has
yes,
only
yes.
60
That's a
gigs
good
of
question
memory.
again. So yes, SSD would be better than to writing to the older types of disks. I believe SSDs are faster to read and write from, right?
Yeah, that's a good
Yeah,
point.
yeah.
I was wondering how much slower it would be. Like, if you have only 16 gigs of memory and you need to process 30 gigs, then is
Right.
that worth it putting that on SSD and using SSD?
Absolutely. So if you can keep your input data set in an SSD, write your final output after you do all your intermediate processing. If you write that final output to an SSD, that would be faster, I believe. Yes, yes.
Thank you.
All right.
In some cases, it may actually even be faster to use a USB 3.0 thumb drive than an older hard drive as well.
Yep.
Just that read-write is that fast.
So we had a couple of questions.
And there
over
was,
here.
yeah, one more down here. I think that's all the time that we'll have after this next question.
Did you have one?
But if you do have... Oh, it was
we'll do two questions.
The lady just down at the end.
Okay, we'll do two questions. We'll start.
Okay.
We'll start with her since I believe she put her hand up first. Okay, there you go.
I'll be quick. I was just wondering if you tested it on data that was on a network drive.
Not these ones specifically. I have done that in the past at a previous employer where I used ArcGIS products, and that was all raster-based processing. And there is certainly an extra delay that's added on by the network, so you do have to consider that.
Yep. So,
However, it's
There was still time savings though, or?
Oh yes, certainly,
Okay.
certainly. And it really, you know, at that point, it really becomes a question of hardware, like how fast is your switch? Are you on, you know, fiber or cable or whatever? So, but that said, there is still certainly performance gains that are possible from it. But if your network is very, very, very slow, then that in effect is causing it to be serial, if that makes sense. So, at that
that would
point,
be
you
your
may-
bottleneck at that
Yeah,
stage.
yeah, exactly.
All right. Oops.
Oop.
Okay.
So I wasn't sure if I was following correctly, but are you able to access everything within ArcPy and utilize that within multiprocessing?
Absolutely. So the only issue you might face combining these modules, the ArcPy and the multiprocessing module, as I said, was trying to send geoprocessing objects across the wire from your main process to those child processes that you have spawned. If you try to do that, you're going to get a pickling error. And in order to not hit those errors, you want to work with simple Python types such as lists, dictionaries, NumPy arrays. All those should work fine. But otherwise, I hope I understood your question properly.
Yeah, I think my just wondering in terms of, at the beginning, you mentioned that you were working back through some, previous code or within ArcPy. I wasn't sure if that meant that certain functions within Spatial Analyst may not be available within.
Oh, well, it's not to make any unavailable, it's to make more available for multiprocessing. So I believe that the reason for that, for what Neeraj is describing, is there's a lot of lambda equations that are being used in the current way that ArcPy is being done, and inherently you can't pickle lambda equations. So by removing those and actually changing them into functions that have a def statement and then are therefore compiled into bytecode, then you can pass those along. So in the process of refactoring, I'm hoping to open up, that to basically have geoprocessing objects be pickleable. There are some considerations that may make a few of the very, very core ones unpickleable, but there's ways to get around that by essentially consuming their properties into a pure Python object and then passing that through and then rehydrating it after the fact.
All right, great. And just a quick follow-on in terms of, you guys are talking about writing everything in memory. Do you have any sort of memory profile or module that you would recommend, or some way to kind of gauge what's kind of feasible? Because I'm just thinking in terms of extremely large data sets, how do you gauge quickly, hey, my machine can, I got to write to disk, or I can write in memory, and if there's just a quick.
Not off the top of my head, honestly. Something I can look into, though, if you want to follow up.
Just yeah. All right, thank you.
Okay. All right.
Thanks
Thank you, everyone.